Now, by the way, there is a very interesting field which is a bit related to motors and actuators. And since we have the time, I'm actually going to spend a couple of minutes on it. And this field is called MHD, magnetohydrodynamics. And what's interesting about this field that in most daily life, the conductors are solid. You have a magnetic field, and you have conductors, and you can make a nice course about what happens when you move the conductors in the magnetic field or the other way. Okay? So that's like classic electromechanics. But there is a subset of that field, and that subset is when the conductors are liquid or fluid. So MHD is the same kind of theory of actuators and motors, but when the conductors are fluids. Okay, that actually has very interesting things. For example, let's say you want to pump, and that's a real problem, which is very, very common. Let's say you want to pump molten metal in pipes. Okay, so let's say you have molten lead or mercury, which is not so popular today, or sometimes sodium, okay? Because actually, okay, so you want to pump it in a pipe, and normally you'll take this pipe and put a pump in it, and that is actually quite a nasty thing. Because first of all, these metals are hot, not mercury, but molten lead, molten sodium, these are very hot. Secondly, there's a problem with this, because once you stop the system, these metals which are hot will solidify, and the pump will be full of solidified metal. You wouldn't be able to restart it. Okay, so it's actually quite a big problem. Now, does somebody know why that is important? Where do you pump, especially these two metals, molten in pipes? It's a very big application. Yes?
Nuclear reactors?
Very true. Because in order to get high efficiency in nuclear reactors, you want to make heat exchangers at high temperatures, and you want to make a multi-stage, say, recovery of the heat. And so usually instead of taking and heating up water, which will need very high pressures to keep it at high temperature, so a lot of nuclear reactors were designed that the first heat transfer is done with molten metal, so you can have a high temperature without needing high pressure. Because to keep water at 320 degrees, you need pressures of hundreds of atmospheres, which makes the system very dangerous. But if you want to transfer the heat with molten lead, lead melts at about 320 degrees, you don't need any pressure. Okay? Okay, so that's very, very attractive to make a heat exchanger with molten lead, and many nuclear reactors use that. Now, where do you have lots of molten sodium? Cooling systems, not just nuclear reactors, but other cooling systems, because you can carry a lot of heat out with molten metal. Okay, and there is many applications. Sodium melts around 100 degrees, so there's lots of applications that actually want the fluid to be liquid metal instead of water, and it has all kinds of advantages. I wouldn't get into it. So anyway, so mercury today is used less, but there are some systems which use mercury as a working fluid. The early nuclear stations, some of them use mercury as a working fluid, again because it boils at a much higher point than water, so you don't need high pressures to transfer the heat. Okay, so how do you pump? So you have a pipe. It has a stuff inside which is usually very nasty. It's hot molten metal, usually a bit radioactive. Something that sounds bad for you. Okay, so and how do you pump it without touching it and without the risk that if it solidifies you cannot restart the system? So looking for a good idea. Yes?
In coils to both heat and create a magnetic field.
And if you create a magnetic field, this is not magnetic. All these metals are not magnetic. Why would the magnetic field affect them?
Be like the copper.
Pardon?
Be like that, yeah, like the copper you drop from the tube. The lens.
it could slow them down. If you put a magnetic field around the pipe, it will slow it down, just like the magnet I dropped in the tube. But you're close. Okay, so the answer is this. If you have a conductor in a magnetic field, if you have a magnetic field coming out of the board, B, so the magnetic field is coming out of the board. If you put a conductor here and you put a current I in the conductor, then you will get some force BLI. Okay? So, this is a conductor. It moves in a magnetic field. All what you have to do is put two electrodes here, insulated from the pipe, or maybe use one section of the pipe, which is non-conductor, put two electrodes, and run a current connected to a battery. Now you have a current flowing inside between these two electrodes. Now if you put a magnetic field this way, there will be a force on this section of the liquid metal. So this force will push it up, but as soon as it pushes it up, new liquid metal will come in. So this will act as a continuous pump without any moving parts. So that's a very attractive idea. Okay? Now let's talk about the opposite. If you fed the metal, if you fed molten metal and you picked up these two electrodes and looked what happens without sending a current through it, it will be a generator. Right? Because this will, a conductor flows through a magnetic field, you'll get a voltage, BLV, and that's a generator. So you don't need to run this molten lead through a steam plant and through a turbine, and the steam turns the turbine turns the generator. You don't need all that. If you want to, if you can run this lead, say by gradients or by any other method, you can make electricity straight from it. So it turns out it's more efficient as a pump. To make it as a generator, the efficiency is not good enough because you can't make the molten lead flow fast enough, right? And if you want to make it flow fast, you need a pump, and then the pump needs energy, so you defeat the purpose. But you can make a pump like that. So this is used mainly as a pump, and it's used in very big scales, like nuclear plants. It's used in very small scales, when you have to do an experiment in the lab and you need a tiny pump. Okay. But this has much more far-reaching implications, because this doesn't have to be a liquid. Any fluid which conducts will work, right? Like water with a bit of ions, with salt will work. But then somebody smart said, just a minute, an electric arc is a fluid which conducts. Because I just explained, inside an electric arc you have ions, plasma conducts. Say flame, if you take two wires inside a flame, the flame conducts. Because inside the flame you have ions, because it's hot enough for the gas to dissociate. So somebody said, why don't we take a jet engine? We take a jet engine with a compressor, and just a regular jet engine, and it shoots out at the back a huge flame. And you can feed it with diesel fuel. Now in this huge flame the jet engine shoots back, we put two big electrodes, like this, and we put a magnetic field at right angles. Now this conducts because that's plasma. Again, plasma meaning ionized gas. But advantage of this, it moves very fast. So a voltage will be generated here, BLV, okay? But V is very high. Because the molten lead, it's not very effective as a generator, it's better as a pump. But here, this comes out, could come out at speed of sound, okay? So V is very high, so even if this is 1 meter, even if L is 1 meter, say this is 1 Tesla, this is 1 meter, but this is 1,000 meters per second, you'll get 1,000 volts. It sounds very attractive. And the electrodes can be very big. You can get like an amp at 1,000 volt. Sounds good. So this is an MHD generator. Okay, and these people built this stuff, but at the end it was less efficient than taking this heat, running a steam turbine. The gold reference is a steam turbine, because you can always take the heat, boil water, and run a steam turbine. Steam turbine, single cycle, is 40% efficient. You can do multi-cycles and all kinds of things, but a normal steam turbine, 40, maybe 50, 40 to 50. So the gold standard, if it's not 40 to 50% efficient, people lose interest very quickly. But the idea is very fascinating, because again, can be done at a very small scale. This works from any scale, from a pipette, from microscopic scale to power station scale. Okay, so anyway, so I got into this because we talked about plasma and arcs. So there is a lot of ideas how to use plasma for sensing, power generation. I'll give you one more example. And some of you actually mentioned that when we talked about blood velocity. One of your assignments was a needle which can measure blood velocity. So some of you actually did mention that if you take a needle, put it in a blood vessel, okay, and you have two electrodes here inside the needle, and two wires coming out, and you put the body or the arm or whatever in a magnetic field. The blood is conductive because it has saline, right? Human blood is 0.9% NaCl, which is enough to make it a very good conductor. Because you don't need much to dissociate and have ions. So if the blood is flowing in a magnetic field, you'll get a voltage, and the voltage is completely linear with velocity. So maybe 5 out of you suggested that in the first assignment, how to measure blood velocity, which is quite elegant. Okay? Because the field doesn't have to be high. Remember, we have it's a low frequency signal. The field doesn't have to be like an MRI machine. It could be quite a small field. You'll get a very small value, because if you plug in BLV, say 1 Tesla, okay, now V, blood velocity, is in the order of 1 meter per second. Okay, and L will be like 1 millimeter. Okay, so even at 1 Tesla, okay, at 1 Tesla you get 1 millivolt. So so if you do that, 1 Tesla is quite a lot to put a body in. It's like MRI is a few Tesla, right? So 1 Tesla is a lot, but if you did that, maybe if it was 0.1 Tesla, you get 0.1 millivolt. That's actually enough. Okay? Now, of course, there are problems. When you do that, there is also some galvanic effect, because this also forms a battery. Right? Let's say you have 2 wires and the metals are slightly dissimilar and the needle is the third metal, so you get also DC voltages because it forms batteries. So how, if you want to measure this 1 millivolt or 0.1 millivolt, and you want to measure it to 1% accuracy, you have to go down, say, to 10 microvolt. So how do you measure 10 microvolts when you have battery effects here, which could be many millivolts? Because any 2 metals in blood will generate 100 millivolt. So you're trying to measure 100 millivolt DC, and you're trying to measure 10 microvolt DC, and you have 100 millivolt of parasitic batteries. So all of you should know the solution by now. And I see one knows, but hold on. I want to hear another opinion. Yes, how?
AC?
AC. So what do you do with AC here?
Oh, you run out of AC out against the magnetic field, maybe?
Exactly. What you do instead of a permanent magnet, the magnet you put the body in is an electromagnet. So if you run this AC, all the battery voltages will stay one polarity. All the BLV voltages will flip. And all that you have to do is have a filter, a high-pass filter, which only allows, it will look like this. The output with AC will look like this. There will be some DC voltage formed by all the batteries, and there will be an AC voltage which flips because the field flips. So you just have a high-pass filter. In other words, you just put a capacitor in series. So only the AC can pass. Okay? That's another good example when we talk about AC and DC and sensors. So this is being done actually. So anyway, it's just a few nice examples to show you that conductors can be liquids, and it opens up a whole field. When conductors are fluids, it opens up this whole field called MHD. Not a lot came out of this field, but you have to know about it if you're ever stuck with such a problem, like how to pump molten metal. There's really no other good way to do it. Okay, so now, so there is one other item I wanted to cover with you before we start on system design, and that item we started last week, but we didn't finish, and that was regenerative braking. So we talked about motors, we talked about braking, and when the motors become large, when the systems become large, people get more and more interested in regenerative braking. So there is regular braking, where you just stop the motor mechanically or electrically, but there is regenerative braking, where you try to recover the energy. You don't just stop the motor. The motor has rotational energy. You try to recover that energy, not to waste it. And the example I gave you is in a car. Let's say you have an electric car. When it goes downhill, you don't want just to apply some braking voltage to the motor, because it just wasted energy. You want to take all this energy, potential energy, MGH, pump it back to the battery. Okay, and that's called regenerative braking, and even electric bicycles now have it. So that's a very important thing. If you have big servo systems which you move huge loads, it has two advantages. It saves power, and it also saves heat dissipation. Because if you didn't have regenerative braking, you'd have to have some big resistors to dissipate all this power. Right? If you have a big steel mill with huge rotational inertias, and you stop it, there's a lot of energy stored. You have to dissipate all this in resistors. You'll need to cool it. So if you do regenerative braking, it's not only you save on the power bill, but you don't need to dissipate all this energy each time you stop. Okay? So to summarize, in a DC motor, I think it's clear to everybody how you do a regenerative braking, because a DC motor, especially PMDC, if you just drive it, it becomes a generator. So there's nothing to do. Okay, so if you have so all the regenerative braking schemes, let's say you have a PMDC. So in all regenerative braking schemes, you have to have a DC to DC converter, because if it's run from a battery, and the battery has a certain voltage, to do regenerative braking, you have to generate a voltage here which is higher than the battery voltage, so the current will flow backwards. Right? When the motor is running, the current is flowing this way, but when you do regenerative braking, even if this is a perfect generator on its own, you have to make the current flow backwards, which means you have to install here, you have to install a DC to DC converter, so it can make any voltage you want from any input voltage, and then you connect it to here. So the input voltage will vary from V all the way to 0, but the output voltage will always be V plus delta V, and where battery voltage is V. Okay, so we will force the current to the battery. Now, physically how this is done is outside the scope of this course, but think of any switching power supply which can take any voltage, like your computer. The power supply can take anything from 90 to 280 volt. It also gives you 12 volt. So it's the same thing. You can do it by DC to AC, then a transformer, and change the pulse width modulation. You can do it even without a transformer, and that's the way it's actually done, is by a smart idea. Then if you take a coil and you run it through a switch, let's say a FET, okay? So if you close this FET, the current will flow to ground. If you open this FET, the current wants to keep flowing because of restored energy, 1/2 Li squared. So because the current wants to keep flowing, the current here, the voltage here will become very high. It's trying to break down the switch. So now you can put a rectifier here and charge it up. So this way, even if this is, say, 5 volt, depending how fast you open the switch, this could be 1000 volt. Okay? And you put another diode here. The purpose of this diode is to close the loop this way. So each time you open the switch, when you close the switch, the current flows this way. When you open the switch, the current flows this way, but it wants to jump to infinity. The voltage wants to jump to infinity because, as I said so many times, the voltage here is L di to dt, and you can make di to dt as small as possible by okay? And by playing around with this pulsing, you can correct the voltage here. So that's one of the simplest converters which can take any DC voltage and make any DC voltage out of it just with two components. Okay? So if you put this thing inside here, you have regenerative braking, which is very good. And the servo amplifiers, which are designed for higher power servo systems, incorporate that. Okay? Good. Now, if there is no magnet, but there is just a coil, it still works. Let's say you have a motor like this, which has a field winding. It still works because this is called a self-excited generator. It has no magnets, but when you start turning it, there will be a little bit voltage generated because there is residual magnetism. So it's a little bit now the little bit of voltage will drive a current, which will make more magnetism, which will drive more current, and immediately it will run up to full current. Is that clear to everybody? Because it's a positive feedback. Because as you recall, in a motor, the field current is much smaller than the armature current. So there is a motor is actually an amplifier. So if you take any amplifier and close it with positive feedback, it will ramp up to saturation instantly. So is that clear to everybody why this will work as a generator even if it has no magnet? Good. Okay. So that's called self-excited. Okay, good. Now, so it's very easy to understand. Now, when you talk about synchronous motors, yes?
Could you repeat the last part?
Yes, because in every piece of steel, there is some residual magnetism, because when this is the hysteresis loop, and when you shut off the power, it doesn't come back to zero. It comes back with some little residual magnetism. Okay? So this, although it has no permanent magnet, has a bit of magnetism, so when you start turning the motor, there's a bit of voltage created here because of the residual magnetism. Now this little bit of voltage creates more current and creates more magnetism, which creates more current, so it's positive feedback. Okay? So that's why even if a generator doesn't have if a motor doesn't have a permanent magnet, it will still become a generator. Especially for parallel wound. It's also true for series wound, but in series wound you have to close the path here so current can flow. Okay? So basically, in all DC motors, brushless DC, it's easy to understand how dynamic braking is done. Because a motor becomes a generator if you just turn it and see what happens. Okay? It takes a little bit more thinking. How does it work in synchronous motors? Okay, so in a truly synchronous motor, it's still easy to understand, because a truly synchronous motor, we said, has a magnet, NS, has coils. So if you don't feed power to the coils and the magnet is rotating, power will come out. Okay? Because it's still a generator. You have a magnetic field rotating on coils, so 3 sine waves will come out of the 3 phases, and they look exactly like the sine wave used to drive the motor. Okay? So here it's even easier than a motor, because in a motor this has the problem that it had problems starting with a load. It had low starting torque, but as a generator you don't care about torque, you are driving it. So if you drive it at a frequency omega, it will generate 3 sine waves, and you get a 3-phase generator, and you can rectify this and run it through this thing and feed the power back to the battery. Now, in the case of AC systems, it turns out you don't even have to buzzer. Sometimes you don't even have to buzzer to feed the power to the battery, because if this is connected to many other motors, let's say you have a 3-phase system, and on the 3-phase system you have many motors. So something interesting happens when it's running as a synchronous system. These are the three phases, RST. You have many motors connected, like say in industry, where the whole country is connected to the same grid. Okay? Now, all these motors are locked to the three-phase grid. Now, if you take one motor and all these motors rotate in synchronism to the three-phase grid. Okay? So if you take one motor and you remove the load, it just will take less power, because this magnet will follow and generate an EMF which cancels out the voltage. Now what happens if you take this motor and not only do you take off the load, you are actually pushing it to try to make it rotate faster. So what will happen, it will induce a voltage which is a bit ahead in phase than the voltage which comes in, and it will actually, because it's a little bit ahead in phase, instead of the currents flowing in, the currents will flow back. Okay? Because let's say that at this point, the phase is a sine wave like this, and this is a point in time. So I'll draw it here larger. Let's say this is the input phase, and we are at this point in time. Now let's say you're turning the motor faster than it wants to turn, so it generates its own phase, which is a bit ahead, like this. Okay, so its voltage is going to be higher than the voltage of the phase connected to it. So instead of the current flowing into the motor, current will actually flow back. So when you have many motors connected to a grid, it's actually, if you want to speed up the motor, you're actually feeding power back to the grid. So it takes a minute that it sinks in, because then you realize that this works like a mechanical gearbox. Because since this is locked to the rotating field, all the motors in the country are locked to the same rotating field. So all the motors in the country which are synchronous behave as if they were geared together. Okay, so that once you start thinking about it, you start realizing that that's the only way the grid can work. Because the electrical grid has these three wires, R, S, and T. Okay, and these three wires are running all across the country. And there are many power stations which share the load. So how can many power stations share the load of a grid? They have to be linked in phase. Right? Because you can't just connect three-phase from one power station to three-phase another power station, even if they're the same frequency. Because if there's the wrong phase, it will be a short. Even if there's a phase difference, there will be a short. So it means if you have a national grid and you have many motors connected to this grid, and then you have many power stations connecting to this grid, okay, and some can be water, some can be steam. All these motors and all these power station armatures behave as if they were geared together on one long shaft going through the whole country. And if you take the load off of one and you try to make it spin faster, all this power goes directly back into the grid and reduces the load on the power station. Okay, so this in big system, synchronous motors, it's very simple. Now if you want to capture the energy, if this is turning at a different frequency than the grid, then you have to put in this DC to DC business. But as long as you want to remove the load and try to speed it faster than the grid, you don't have to do anything. Because it's all synchronized as if it was on one big shaft. Okay? And that's how the electrical grid works. All of North America, not just Canada, all of North America is connected as if on one big shaft. All the motors, all the generators are in phase. Okay? Otherwise it can't work. Otherwise you cannot have a national grid. Is that clear to everybody? Yes.
Actually, never mind. I'll think about this then.
Okay, think about it. It's again a bit beyond the scope, but it's very interesting stuff. So in big systems, this whole regenerative braking is a bit different thinking. Okay. Now the last thing I want to raise is how do you do regenerative braking in an induction motor? Because that's actually very tricky. Because an induction motor is not phased to a grid, but on the other hand, an induction motor doesn't have magnets. So remember, the induction motor works because the armature, which is shorted, is always lagging behind the grid. So induction motor has an armature which just has a shorted coil, so it creates induced poles by induction. Okay, so what happens if I take all the load off? So if you take all the load off, it will still have to slip a little bit behind the synchronous frequency, because otherwise there will be no induced current. Remember the graph for this thing, if you draw, say, torque and omega, if you draw it in this way, this axis looks like this, or if you draw it, we drew it the other way, we drew it torque versus omega, we drew it like this, but it's the same graph. So if you take off the load, it's going to sit about here, which is very, very close. Sorry, backwards. Sorry, both are backwards. So if I draw torque versus omega, it will be like this at 0 torque. I'm confusing myself now. Okay. If this is torque, this is omega, it will look like this. Okay. So basically, if you reduce the torque to 0, it will almost hit synchronous speed. There'll still be a tiny bit of slip, because if there is no slip, it can't induce a current. Okay? Now, what happens if you take this armature and you force it to go faster? In other words, you reverse the slip. So if you force this to go at the synchronous speed, then no power will be transferred, because it doesn't work as a transformer, because if this is omega synchronous and you force this to rotate at omega synchronous, it sees a constant magnetic field, because they're both working together. If it sees a constant magnetic field, there is no induced current, there is no power going into the motor. So the first part is easy to understand. If you force this externally to follow the rotating field, no power will be transferred into the motor, except losses, but actually no power will be coupled to the rotor. But what happens if you force this to go faster than the synchronous speed? So you are reversing the direction of the slip. This is now moving faster than the field. So strangely enough, power will flow back. And the reason power will flow back is by the same argument here, that if you have two sine waves, okay, and one is leading the other, depending which one is leading, which one is lagging, power will flow this way or this way. So normally there is a power angle, and this is lagging the three phase, so power flows in. But if you reverse the power angle and it's leading, power flows back. So the same argument works here too, but instead of power angle, you have to reverse a slip. You have to make this go faster than the rotating field. Then there is a slip, there is induced current, but the induced current is trying to generate an EMF which is actually leading in phase, and because the EMF is leading in phase, the current flows backwards. Okay, so imagine if this is the input voltage, okay, and you manage to turn this faster, and momentarily there was an EMF which was higher than this voltage. It's only higher because its phase advanced, like this. So momentarily, it will actually feed the power back. So if you continuously feed it, that this EMF is at the right phase and higher voltage, power will flow back. So even in an induction motor, if you overdrive it mechanically, it can feed power back. And that's how it's done in electric cars. That's how the Tesla works. And the way it works, because there is no synchronous speed in an electric car, because the car can go at any speed. Okay? So the way it works is, as soon as you put your foot on the brake pedal on a Tesla, or you drop the acceleration pedal, there is an encoder on the motor. There is a shaft encoder which measures the actual speed of the motor. So at any given moment, once you know the actual speed of the motor, what you do is you generate a rotating field which is slower than the motor, because you can control the phase and frequency of these three coils. So you generate a rotating field which is always, say, 10% slower than the motor. So at any speed down to 0, the armature is always ahead of the rotating field. And because it's ahead of the rotating field, the power flows backwards. I know I didn't spend enough time explaining it in detail, but it's way beyond the scope of the course. But what I wanted to show you is that you don't necessarily need a permanent magnet to make a generator. The generator can be self-excited by many different ideas, starting by this idea in DC motors, or starting by more sophisticated ideas of being ahead of the rotating field and feeding power back. But because this one, the induction motor, doesn't have a magnet, and this one doesn't have a magnet, okay? But it still can feed power back to the grid, and this is only important in big systems, or systems which have to be super efficient, like an electric bike, okay? But in a normal servo, unless it's a multi-horsepower servo system, you don't bother with it. Because you see, if you want to brake, you just dump the energy into a resistor, okay? The only exception I can think of is electric bikes. Like if you have an electric drill with a battery and you stop the drill, there is no regeneration because it's not worth it. Also, there's not much inertia, okay? But in electric bike, the new ones, it is worth it because you go a long way uphill, you want to recover some of this energy downhill. Turns out you can recover 90% of it. Because if you really do a very good job with a DC to DC, this DC to DC is like 95% efficient. A generator is like 95% efficient. So 95 times 95 times battery is 90% efficient. So if you really do the math, even for an electric bike, which is well designed, you can get 0.95 times 0.95 times 0.9, which is the battery. So you get overall maybe 80%, but it's not bad at all. Okay? So most of the energy does recover to the battery. Okay, so this is regenerative braking, and so we'll start system design on Thursday, but I just want to make sure everybody here really understands the basics of electromechanical systems. So if somebody here doesn't understand why there is a spark when you disconnect a load, or if somebody doesn't understand any of the basics, that's the time to ask, because we're not coming back to that. It's better to ask now than not understand it on the exam. So, is there anything about motors or actuators or the whole course that you had some doubts about? Okay, good. Now, all this theory, which we always talked about, electromechanical actuators, about sensors, motors, all this theory also applies to hydraulic and applies to pneumatic. It applies to, because the basic concepts are the same. If you have, let's say, a hydraulic servo, and you have a pressure accumulator. The pressure accumulator behaves like an inductor. It stores up energy and has all the same problems. If you want to shut off the flow right away, it doesn't let you. The pressure goes up suddenly. And basically, any other servo system which is not electric, if you understand how an electrical servo system works, you can easily make the conversion between electric and non-electric. You have to remember that the conversion is that what's called current in an electric servo is called flow in a fluidic servo. What's called pressure in an electric servo, what's called voltage in an electric servo is called pressure in a fluidic servo. So now you can use the same equations. Okay? So for example, if you have a fluidic servo and you have a So if you have a fluidic servo and you have a container okay, and you have, say, a pump. Okay, let's say the pump will be like the battery which feeds water into the tank, okay, and let's say you shut off the water supply immediately, okay, or let's even say before you shut off the water supply, you have a back pressure because of the height here, okay, and the back pressure is the same as the back EMF. The pump pressure has to overcome the back pressure in order to make a flow. So it's the same as back EMF in a motor. If you shut off suddenly the water flow, what will happen to the pressure? So this is P, these are pressure gauges. Okay? So what happens if you shut off the water flow momentarily? What will happen to this pressure? What will happen to this pressure? Let's say they were both reading a certain pressure while the pump was working. This was a tiny bit higher than this, because a pipe is a bit like a resistor. But now you shut off the water flow suddenly. What will happen to the two pressure gauges?
One will spike and one will
Okay,
rise and one will drop.
so which will raise, which will drop?
The one on the pump side will raise.
Will raise. Now, why would it raise?
Because it has all this flow that's kind of compressing.
Yes, because basically the pump has some graph, flow versus pressure, and most pumps, if this is pressure and this is flow, they have some graph like this, so if the flow goes to zero, the pressure goes up. Okay, but what happens at the moment when you stop? Just at a millisecond when you stop. So steady state, if you stop it, this is P1, this is P2. If you stop it, P1 will be bigger than P2 because of the characteristic of the pump, which is the same as a battery or a motor. Okay, but what happens at the moment you stop?
We have a water on there?
Exactly, you have what's called a water ram, a huge spike in pressure. So if you look at the graph, this is time and this is pressure. So you had, if you look at P1, you had this, and you know later on it will be higher, but at the moment of stopping you'll get this. You'll get a huge spike in pressure. And why is that? Inertia, because this water wants to keep flowing. You stopped it. This water has stored energy, 1/2 mv squared. All this stored energy suddenly stopped, has to go to zero. So it has to convert to some huge spike in pressure, right? Because the pressure times the displacement is energy. So does this remind you something? It's exactly the same as a motor with inductance. And if you look at the circuit now and you say, okay, this is really like a battery. You have an inductor, you have a switch, you have a resistor, you have voltmeters. It's exactly the same thing. In this case, the energy is stored here, Li squared. Here it's stored mv squared. So if voltage is pressure, the voltage here will have to jump up when you open the switch and so on. So you can see, if you all these concepts of back EMF, voltage, spikes, energy has to dissipate, if you understand them in one servo system like electromechanical, it only takes you a few minutes to apply it to a non-electrical servo. Okay? So remember again the analogy, because the only non-electrical servo you are likely to have to work on is fluidic. I mean, there's other things, but you're not very likely to work on them. So remember the analogy: in a fluidic servo, pressure is the same as voltage, flow is the same as current. The static pressure here is basically a voltage. It's like a back EMF in this case. And the curves of the hydraulic motors and pumps are exactly the same as the curves of electric motors. Except in here it's all DC. There is no AC fluidic systems. AC meaning the fluid goes back and forth. It doesn't exist. The nearest thing to an AC fluidic system is something they do in hydraulic servos called diesel. They do it also in electrical servos, but mainly in hydraulic. Does somebody know what diesel is? That's a very clever idea, actually. See, hydraulic servos have a lot more stiction than electrical things. Because the nice thing in electrical servos, the electrons can flow very smoothly. Whenever you start the smallest current, the electrons start flowing, or smallest voltage. But a hydraulic system, when you have valves and pistons, there is static friction. You increase the pressure a little bit, it doesn't move. Just like stick in mechanical systems. Right? You have to overcome static friction before things start moving, and that causes some backlash in a servo. A bit like hysteresis, right? If you have a piston, you want to make it go one way, you increase the pressure. You have to have a certain minimum pressure to make it start moving. Now you want to make it go backwards, you have to reverse the pressure and go a little bit below zero, right? Otherwise there is some static friction. And that's very bad for a servo, because we talked many times how bad backlash is for a servo, or hysteresis. So every hydraulic system with pistons and stuff has built-in hysteresis because of the difference between static friction and dynamic friction. So the way you solve it, you put a small AC signal into the servo. So let's say you have a pump here, and that pump just gives you a pressure pulsation, or a sine wave, small variation in pressure. So what this means, that wherever you have some pistons in the system, these pistons are always vibrating, so they don't have static friction. Okay? And that's a very powerful technique. Without that, you cannot actually build a high-performance hydraulic servo. So that's called Deezer, and that is also used in electrical servos. If you need a very precise servo, like I say, it's used in gyroscopes or things where the smallest amount of friction can cause a problem. Like if you want to make what's called an inertial navigator, which is based on a gyroscope, you have to integrate the acceleration twice to get to position. Because the gyroscope will measure acceleration, or you have to integrate it twice, you get to position. But if you have a very small error, static error, and you do a double integration, this error will grow to infinity. So if you have some mechanical systems, you also introduce Deezer. You want to take out any static friction. But in hydraulic systems, it's almost impossible to do without it if you want a very high performance servo. So this is the only time where you'll see something equivalent to AC in a hydraulic servo. Anyway, that's just an example that a servo doesn't have to be electrical. Yes?
Doesn't the mechanical device have to go through a point where it stops? You know, the thing moving up and down, when it changes direction, it has to stop.
No, because it stops momentarily, but it's not enough to build up static friction. It vibrates. Any sine wave goes through 2 points. It stopped in a cycle, but because it's still in motion, okay, the velocity is zero. The velocity is zero, but at the point the velocity is zero, the acceleration is not zero. So basically, it doesn't really get static friction. Okay? You see, twice in a cycle the position is zero, twice in a cycle the velocity is zero, but it's not the same points. Okay, that's what prevents static friction. Okay, I have to